In this video, we'll go over some more examples of related rates problems. Here's our first example. Car A passed through the intersection at 1 p.m. at a speed of 48 miles per hour heading north. Car B passed through the same intersection exactly 1 minute later, so at 1:01 p.m., at a speed of 45 miles per hour headed east, and both cars continue at the same speed and direction for the next 10 minutes. At exactly 1:05 p.m., how fast is the distance between the cars changing? A lot of words there. Let's start with a picture. So we'll say there's our intersection. Car A is driving north, and car B is driving east. There's our basic setup. We know some information about who is where. Well, let's get the basic picture up first. So what do I actually care about here? I am being asked about the distance between the cars. So I should draw in the distance here and see what I can do with this. Well, this gives me a right triangle. It's a right triangle. I also want to label certain things in my picture that are changing, and things that are changing are the lengths of these sides. So we'll label this with little a, this with little b, and the hypotenuse with little c, as we should. That's all I really have at this point in terms of a picture. Now, what's an equation that relates my three variables a, b, and c to each other? Pythagorean theorem. So I know that c squared should equal a squared plus b squared. Great, sure, there's an equation we can start from. Are any of a, b, and c fixed? The answer here is no, they're all changing because the cars are both driving, and this is also changing between them as well. So, if I want to try to solve this problem, I have to differentiate now. Anything I plug in here is going to be a mistake. So let's start by differentiating this equation. So we have c squared equals a squared plus b squared. I'm differentiating that in time. Let's take that derivative and see what we get. All these are chain rule type problems. So we're going to get 2c dc dt equals 2a dA dt plus 2b dB dt. Now my goal here is to solve for dc dt, because that's the distance between the cars. So I have the following expression. dc dt equals 2a dA dt plus 2b dB dt over 2c. I can also then cancel all the 2's. Great. Now I can plug in numbers. What do I know from my problem statement? My problem statement tells me that car A is driving north at 48 miles per hour. That means that dA dt is 48 miles per hour. So I can plug that in here. I also know that car B is driving east at 45 miles per hour. So dB dt is 45 miles per hour. So I can plug that in. I'm still missing A, B, and C. How can I find A, B, and C? Well, so we're looking at exactly 1:05 p.m. That's where this fact here comes into play. So at 1:05 p.m., how far is car A from the intersection? Well, car A has been driving at 48 miles per hour for 5 minutes. They passed the intersection at 1 p.m. So A is 48 miles per hour times 5 minutes, which is 1/12 of an hour, which is 4 miles. So A is 4 miles, we can plug that in. What about B? Well, car B has been traveling east at 45 miles per hour for 4 minutes, because they passed the intersection 1 minute later. So B is 45 miles per hour times 4 minutes, which is 1/15 of an hour, which is 3 miles. We can plug that in, like so. What about C? Now that we've found a derivative expression, now we can figure out what C is using the fact that we know that A is 4 and B is 3. So if A is 4 and B is 3, this is a 3, 4, 5 right triangle, so C is 5 miles. I can plug that in. And now I can solve for my rate because I have everything I know in this equation. So this is 4 miles times 48 miles per hour plus 3 times 45 miles per hour over 5 miles, which comes out to 65.4 miles per hour. That's one problem, how to solve it. The basic idea is figure out an equation, differentiate it, and then see what you need in that final expression to solve the problem. Go back to your data, figure out what those values actually are, plug them all in, and calculate your final answer. Our second example here, a person's watching the launch of a model rocket from 50 meters away. The rocket takes off vertically. When the angle of inclination of the rocket is pi over 6 radians, the angle is increasing at a rate of 0.8 radians per minute. How fast is the rocket moving at that moment? Again, let's start by drawing a picture. There's a rocket, there's our person. What do we know from the problem statement? The length to the launch point is 50 meters. Is that value changing? The answer is no. The person's not moving horizontally. They're staying right there. So that length is always 50 and that can stay there. We know the rocket's moving vertically. And we're told something about the angle of inclination, so I should draw in this line here, because here, theta is the angle of inclination. The other thing that's changing here is the height y, because the rocket's moving upwards. There's my picture. I'm told about a certain value of theta and a certain rate of change of theta, but that's not important yet. The first thing is an equation that connects y to theta. In this case, our best bet is tangent, because tangent of theta is y over 50, or y equals 50 tangent of theta. If that 50 was changing, it had to be a variable, and things get a little more complicated, but since it's not changing, we can do it just this way. Now, I want to differentiate this expression in t. So I have y equals 50 tangent theta. I want to differentiate in time. And if I do that, I get a dy dt on the left. And on the right, I get a 50, the constant, rid of tangent is secant squared, and then times a d theta dt. What do we need to solve this out? Well, I need the value of theta and the value of d theta dt, both of which are given in the problem statement. So I'm good to go. dy dt should be 50 times secant squared of theta, which is secant squared of pi over 6 radians, times d theta dt, which the problem statement said was 0.8 radians per minute. So now I can figure this out. 50 times the 0.8 gives me a 40. Secant squared is 1 over cosine squared of pi over 6. Cosine of pi over 6 is root 3 over 2. So this is 40 times 1 over 3 over 4, which is 160 over 3 meters per minute. This is an example of setting up a related rates problem, setting up an equation now involving a trigonometric function, taking the derivative, and then seeing how to manipulate it to get to the answer you need by plugging in numbers you know from the original problem statement.